Hey there, I see that you're back for some more awesomeness as we go deeper into trig substitution. In this video, we're going to do 3 examples so that you feel really strong with this. We're going to look for the Pythagorean substitutions that we can do. Let's dive. So, we're given the integral of, with respect to x, over x squared root 4 minus x squared. Now again, u substitution won't work here, our other processes won't work, so this is a last-ditch effort using the trig sub, but it's gnarly. So we look at this, and we say that's Pythagorean. So I'm going to draw out my triangle. And I always draw the same kind of right triangle. I'll call this angle theta, just to be consistent. And now, if you're given something minus something, if you think about it, you have a squared plus b squared equals c squared. If you're given something minus something, we must have done like a squared equals c squared minus b squared, and solved for one of the legs. That's the only way we can get that, which means that the 4 is going to be the square of the hypotenuse, right? So this hypotenuse is going to be 2, right? Because it's a squared, or rather c squared in this case, minus a or b squared, doesn't matter. That's going to just be x. So again, look at that as the square root of 2 squared minus x squared. And I put x always opposite theta just to be consistent. You don't have to, we could have put it there. Now, from here, what we've got left is we need to find this length. Well, that length is the square root of this squared minus that squared, or the square root of 4 minus x squared. Now, here's what's pretty cool about all of this. We've got a way now that we could substitute in for individual pieces. So the first thing I'm going to substitute in for is, I want to substitute in for root 4 minus x squared. So what's the easiest ratio I can see getting that? Well, you've essentially got 1 over that number. The closest I can get is 2 over that number using that triangle, right? We're restricted by the triangle. So that's 2 over 4 minus x squared in the square root. And now we look at the ratio. Now normally it would be cosine, adjacent over hypotenuse, but it's the reciprocal, so that's secant theta. But we don't have a 2 there, so either you're going to put a 2 in the problem and then divide by it, or we can divide both sides by 2 and get the exact substitution. It doesn't matter which way. I'm going to divide both sides by it just for fun. Either way, we could have made it happen. Could have put a 2 there again and a 1/2. You'll see that it works out to be the same. So this is going to be multiplying both sides by 2. All right, so we've got dividing both sides by 2. Of course, right? You're solving to get that 2 over here. So 1/2 secant theta is that. So we go piece by piece and we build it. So 1 over root 4 minus x squared is 1/2. I like factoring out the coefficients. I talked about that in video 1. Secant theta. So what we've now done is we've accomplished this part. But now we need a number over x squared, 1 over x squared. The closest I can get over with that is 2 over x. That's a number over x just on its own. And that's equal to, well, sine would be opposite over hypotenuse. This is hypotenuse over opposite. So that's the reciprocal cosecant theta. Okay, we're going to do 2 things here, though. We want 1 over that number. So again, 1 over x equals cosecant theta over 2, or 1/2 cosecant theta. And then we want it squared, so we're going to square both sides. So it's 1 over x squared equals 1/4 cosecant theta. So another manipulation, but we now have this, and we now have that as our substitutions. The coefficient of 1/4, I again will factor out. I'm going to take that out of there, because I can. And this is going to then just be cosecant theta. That gets me 1 over x squared. Oh, but we still have dx to substitute in for. We've done the 1 over x squared, the 1 over root. How do we get dx? It's a number of ways, but the easiest way is x over 2. So we'll do x over 2, and that's equal to sine, because it's opposite over hypotenuse. Now we want dx, and just dx on its own. So I'm going to take a derivative. That's 1/2 dx equals cosine theta. And then I'll multiply both sides by 2, so dx is equal to 2 cosine theta. All right, so at that point, we're in pretty gnarly shape, right? We're in really good shape because dx is now 2 cosine theta. So now I'm going to multiply by 2. I'll squeeze that in there and multiply by cosine theta, d theta. Oh, okay, I see what we're working with. Well, cosine theta and secant theta completely divide out, and that's pretty sweet. So now what we're left with is the 2's dividing out, and 1/4. And then you got the integral of cosecant theta. Okay, so this one's kind of an interesting integral. The integral of this one is either you memorize it or you don't. And so some teachers won't ask for this problem because of that. But it's going to be ln of cosecant theta minus cotangent theta. That's it. And some people will actually, and I know that was a weird edit right there, some people will actually take this, and some people memorize that as minus ln of cosecant theta plus cotan theta. So the way that I actually originally had it was fine. Ln of cosecant theta minus cotan theta, or minus cosecant theta plus cotan theta. Both are correct. I'm going to go with, I just want to put that one in there, this original interpretation here. So now what we do is, we now need to substitute in for these theta values, cosecant theta, using the triangle. It's going to be a mess. So we get 1/4 ln of the absolute value. Cosecant theta is 2 over x, right? It would be the reciprocal here of sine. 2 over x, just using your triangle, minus cotangent theta is adjacent over hypotenuse, root 4 minus x squared all over x. And that's all that that problem has for us, plus c. And you could join that up over one fraction. I'm not going to. That's your answer. So once you get to your trig functions, you use your triangle to resubstitute back in. A little bit more involved than what u substitution would be. All right, so pretty tough just because of the integral. Let's do 2 more. It's going to be a longer video, but we got this. In this one, we've got root x squared minus 9. Let's go. We've got our right triangle. And so now you've got, well, this is almost like it would have to be a hypotenuse, right? Just like I went over before, the square root of c squared minus a squared or b squared would be equal to b. So that's your hypotenuse, something squared. So that's going to be x, here's theta, minus this value right here, that's 3. I'm going to put the, I don't know, we'll put the coefficient here just for fun. And then this side right here is going to be the square root of x squared minus 9. Literally doing the Pythagorean theorem to find that. So now we're going to use all of this for our substitutions. So first, we need the square root of x squared minus 9 over x. That's right here. That's literally sine, opposite over hypotenuse. So we see that sine theta gives us that exact substitution. And isn't that just gorgeous? Oh man, it's perfect. All right, so we get that. So that is the exact substitution. So I get the integral of sine theta, but wait, there's more. We need to figure out what dx is. To find dx, I'd have x over 3, right? So what's x over 3? Well, x over 3 is equal to, this is pretty cool. This is going to be equal to secant theta, right? How do we get that? Well, because that would be, again, dx is what you want. Let's get the x on top to find that derivative. That would be the hypotenuse over the adjacent, that's secant. So x is equal to 3 secant theta. So dx, when we take a derivative of both sides, is equal to, 3 secant theta tangent theta. Oh my goodness, right? Because that's the derivative of secant theta. So not so bad right there. Now, from here, we're going to be rocking and rolling. We're going to see how this thing is going to go. So what I'm left with is 3 on the outside. We've got a secant theta times a tangent theta. And a very interesting thing happens here. And the integral is almost too perfect. It's hard. It's a hard integral. But watch this. I'm going to write everything in terms of sine and cosine before, because nothing really cancels nicely. I get sine theta times 1 over cosine theta. Times, wait a second, sine theta over cosine theta. And you might be like, what do you mean, wait a second? Well, here's the thing. That, as we take a look at it, is sine squared over cosine squared, or tangent squared theta. Now, why is that important? Because tangent squared theta, and we saw this actually in the previous videos, right? In the previous lesson, can be rewritten as secant squared theta minus 1. That's why it's so important you know trig integration before you use trig substitution. Now, the integral of that is not so bad. So this is something we've been trained on now. Get that even function of tangent. Breaking it down with our secant squared identity. The integral of secant squared is tangent. We're ready to integrate here. So it's 3 times tangent theta minus theta. Okay, plus c. Now, we're going to use this triangle to substitute in terms of x. So we're almost done. We get 3. Going to distribute that to both of them. Tangent theta is the opposite over the adjacent. So it's 3 root x squared minus 9 all over 3. Opposite over adjacent. Minus theta. How do we get theta? That one's going to be interesting. So we can get theta a number of ways. I'm going to look at this just to make things not so confusing and think about it this way. We've got, well, a multitude of ways, but I'm going to use this because it's the easiest way, I think. I could take arcsecant of both sides. That would work. So I get arc secant of x over 3 is equal to theta. That solves that out. You could also have done tangent inverse of that. So I'm going to have plus arc secant of x over 3 plus c. Or I'm just going to kind of put down that we could also have done any number of inverses. We could have done arc sine, right? We could have done arc sine of root x squared minus 9 all over x. And then we could have done arc tan of opposite over adjacent. A number of ways that we can get theta. They all work. Actually, six ways you could get theta. All right, now I should correct it though. That's a minus sign. It should not have become plus. All right, now into the final problem in this video. Oh my goodness. Well, first and foremost, it's nasty the way it looks. So let's kind of rewrite this as dx over, now it's the square root of all this stuff, right? It might be easier if we just write it as x squared plus 36, and we'll write that to the 3/2. Let's see what that does for us. So, looking at that though, I still have something Pythagorean. I've got theta, I've got x and 36, so that's x squared plus 6 squared inside of there. So I'm going to put the 6 here, because if it is a plus, they're both legs in the triangle, and an x here. And then this would be the square root of x squared plus 36. Oh, let's get there. So what we have here is, and I think it's easier if we look at it this way, if we look at it instead as 1 over, or dx over, the square root of x squared plus 36 cubed. So I rewrote it like that and then thought, ooh, we got the square root, let's keep it in there. And now when we do that, oh my word, watch how this thing opens up. So we need the ratio of a number over this, and then we're going to cube it. So that's going to be, well, a number over that. The closest I can get with that triangle is 6 over root x squared plus 36. And that's equal to cosine. So that's cosine of theta. But then I don't want the 6 there. I want it to be 1. So I could either put a 6 here and then a 1/6, but I got to cube both sides too because we're cubing it, right? So let's do this. Let's move the 6 over. We get root x squared plus 36. That's going to be equal to 1/6 cosine theta. But again, we're not quite there. We want it cubed, so we cube both sides. 1 over the square root of x squared plus 36. All of that cubed. And 6 cubed is going to be equal to 1/216th cosine cubed theta. Oh. So that's going to get factored out, but all of that is equal to this. So I get 1 over 216. Nice. And then what's left is cosine cubed theta. All right. So let's see what we got left. We got dx that we need, so I'm going to box this. It's one bit of logic that we did. Change up the color, because why not? We've been doing black the whole time. Let's change it up. So now we need dx. The best way to get dx is take the derivative of just plain old x. So that's x over 6, which is going to be tangent theta because that's opposite over adjacent. Take the derivative, but I also just want dx, so that's going to be 1/6 dx equals secant squared theta d theta. Watch how sweet this ends up being. I multiply both sides by 6. dx equals 6 secant squared theta, sorry, d theta. And that's our substitution for dx. So I'm going to factor out the 6, and I end up with secant squared. Now, why do I like secant squared so much? Because cosine cubed times secant squared, that's like dividing by cosine squared. 2 of those powers are going to divide out. You're going to be left with, that's 1 over 36, 6 into 216, 36 times, cosine theta. And again, that's because secant squared times cosine cubed is cosine theta. That's beautiful, because the integral of that, oh, it's just sine theta plus c. And so it ends up being relatively easy, but we got to substitute back in terms of x. What's sine theta? That's the opposite over the hypotenuse, which is x over root x squared plus 36. And that is just a gorgeous problem right there, plus c. That's it. That's all we got for that problem there. That gives you a litany of the types of problems that could be given to you. Again, look for that Pythagorean triangle relationship that you got going on there. And then you're looking for substitutions that will substitute from the triangle using trig functions that match those ratios that are in here. It's awesome. I'll see you in the exercises. We'll get stronger in it there. I promise you, practice does make perfect here. Until then, be well. Peace.